In this video we will explore in some detail the fundamentals of power, torque and gearing to discuss their effects on a car's acceleration. This topic is subject to a lot of confusion and misinformation, and popular wisdom of car magazines and media in general tends to add to it instead of clarifying the issue. By going through the underlying physics and analyzing several practical examples, we will shed light on this contentious issue. You do not need a degree in physics to be able to follow this though. Don't get discouraged if you don't understand the formulae. They are not required for understanding the more important principles. And if you do follow, that only means you're awesome. The job of a combustion engine in the car is simple: to turn chemical energy into kinetic energy, to turn fuel into movement. First, we need to establish the very basics. Kinetic energy is what determines an object's velocity or speed. It is calculated by multiplying the mass of the object with the square of its velocity and divide by 2. Notice that because of the squared velocity, adding speed at low speeds requires very little energy, but a lot of energy is needed when the object is moving fast already. Power is how much energy is produced per unit time. The units of power are watt, joules per second and newton meters per second. When it comes to car engines, common units are horsepower, kilowatt and PS. Engine torque has the unit of newton meters or foot-pounds, which has the same unit dimensions as joules and thus energy. And this is where a lot of the confusion of what accelerates a car, power or torque, stems from. Let's take a look at the difference between torque and energy. Torque is exactly what most people believe it is: a force of 1 Newton pushing a 1 meter long lever perpendicular to the force. It creates a torque of 1 Newton meter. This measure varies drastically over the course of the combustion cycle and is not a meaningful measure of an engine's performance. It is important to the engineers who have to calculate stress and wear within a car's drivetrain though. What is relevant to accelerating a car is the work produced by the engine, which in this example is the force of 1 Newton pushing the lever 1 meter along its curved path. Work is equivalent to energy, and as we have seen in the basics, we need this energy, the work produced in the combustion cycle, to give the car velocity or to accelerate it. To give you an example of the difference in these two concepts, if you lean against a wall, you create a lot of torque, but the counterforce is as big and nothing moves. You don't accelerate anything and create no kinetic energy. If you, on the other hand, lean against a little boat, you create the same amount of torque, but the counterforce doesn't match yours and the boat accelerates. You have created work and probably got wet in the process. With this knowledge, let us hammer down what accelerates a car. If you want to jump over this derivation, just click the link on the screen right now. So far, we have established that we need energy in order to make an object go faster. To determine how much energy we need to increase a car's velocity, we add a tiny amount of speed to the initial velocity v0 so that the car accelerates from v0 to v1. We call this difference in velocity delta v and make its value very small. By subtracting the car's initial energy from the energy it has after the acceleration, we get this expression. Substituting v1 and developing its square, we realize that delta v squared is completely negligible because we made delta v a tiny number. It turns out the difference in kinetic energy is the mass times v0 times delta v. We can now use the expression we just arrived at and combine it with the basic definition of power is energy per time, rearranged to energy equals power times delta t. Before we combine them, it is important to know that acceleration is defined as an infinitesimal change in velocity divided by an infinitesimal change in time. If we look at a snapshot of acceleration, This does apply to our delta V and delta T. Alright, enough of these technicalities. Now we just put together the two different expressions for kinetic energy and arrive at the final answer to our question: what accelerates a car? Acceleration is power divided by mass times velocity. More power means more acceleration. More mass means lower acceleration. More current speed means lower acceleration. And more torque means nothing? Not quite. Torque as in the amount of work produced per combustion cycle and not the static force and lever becomes an interesting measure when we take into account gearing. So what about gearing? Let us consider having a standard manual gearbox with fixed gear ratios fitted in the car and work out the acceleration from there. Again, you can jump over the technicalities if you want to. Power is energy over time, but in car terms can also be expressed as torque, T, times RPM, here denoted as R, times a constant, here called K. Again, I want to point out that we are talking about torque in the sense of work and energy and not actual torque. Within a fixed gear ratio, the engine RPM becomes directly linearly connected to the speed of the car. Within that gear, if you accelerate from 30 to 60, the RPM doubles. This means we can express R as the velocity times a gearing constant, G. Using our previously derived equations, we see that acceleration within a fixed gear now becomes torque times a constant divided by the car's mass. To summarize, we have shown that the acceleration of a car depends only on its current power output, its mass, and its current speed. If we look at the subcase of accelerating within a fixed gear ratio, the first statement still holds true, but also the limiting effect of the gearbox means that we get an acceleration that is directly linearly proportionate to the amount of work the engine produces per combustion cycle, what is wrongly called torque. Constant torque means constant acceleration. More torque implies more acceleration. It is the limiting effects of the gearbox that deceive us into thinking that torque is what accelerates a car. That is not true, as we have just seen. This is the point where the physicist would just call it done, walk away and leave normal people standing perplexed with nothing to hold on to. Although I am a physicist, I'd like to illustrate these concepts we just explored and put it all into practice to see what comes out of it. Practical example number 1, the idealized engine. Our first example is a simple idealized engine which produces a constant amount of energy per combustion cycle, or torque. Locked in a fixed ratio gear, when the car goes twice the speed, the engine spins twice as fast. Hence, the idealized engine will produce twice as much power when the car goes twice as fast. This doubling in power offsets completely the additional energy demand from the higher speed and keeps acceleration constant in this example, where we do not consider any air resistance, in order to keep things simple. Also worth noting is that from what we have derived, it directly follows that you would want to rev this engine as high as you can at all times in order to get the maximum acceleration out of it. You would want to gear it such that it revs as high as possible to make the maximum power. Real-life engines have a lot of problems revving higher and higher while keeping up producing the same amount of energy per combustion cycle. A gearbox is needed to help work around this limitation. With just a single fixed gear, a car with a combustion engine would not perform well because it limits the range of speeds a car can drive. To illustrate this, we take the idealized 100 Nm engine as example, accelerating a car from 20 to 60 using the 2000 to 6000 RPM range in first gear. Acceleration remains flat throughout that gear. We also see that acceleration in higher gears in the same rev range are lower overall. That is because the engine runs at lower RPM, which means it is producing less power at the same or higher speeds. It is important to note that ideally a gearbox would keep an engine at peak power RPM at all times in order to maximize acceleration. In that case, the car's starting acceleration would be 3 times higher with a gearbox that accomplishes this, because acceleration at lower speeds takes so much less energy. There are transmissions that can run the engine at maximum power. They are called continuous variable transmissions, or CVTs. Unfortunately, they suffer from significantly more friction losses compared to manual gearboxes. A very similar effect is that of electric engines, which have constant power across their rev range. By showing only the rev range used when each fixed gear is revved out before shifting, we can see how the gearbox helps running the engine close to the maximum RPM and power in each gear. The takeaway here is, for maximum acceleration, you want to maximize engine power at all times. The gearbox is used to stay close to maximum power throughout the range of speeds a car can achieve. Electric engines naturally achieve this, while CVT gearboxes make possible to stay at a combustion engine's peak power RPM across all car speeds. Practical example 2. Realistic engine and drag. Let's take a look at a more realistic engine, a small performance motor with around 100 Nm of torque to stay comparable to the idealized engine in example 1. Notice the characteristic shape of the torque curve and see if you can find it in the acceleration graph from this engine using a standard manual gearbox. In fact, every gear's acceleration curve is a compressed or stretched image of the original torque curve. Again, remember that this is because of the limitations that come with fixed gear ratios and not because torque is what accelerates a car. Let us complicate matters a little by making things more realistic. If we add aerodynamic drag into the mix, the acceleration curve in each gear is bent downwards as the car's speed increases. Drag is quadratic in nature. Going twice as fast means 4 times the air resistance, which is why at higher speeds the acceleration lines are bent downwards stronger. With this more realistic picture, and using this example, we can start to talk about gearing and optimal shifting to maximize acceleration. Let's take a look at this specific example and point out a few things about it. Acceleration is the highest in first gear as long as it is available. This is because even at the red line of 9000 RPM, the engine still produces 66 kilowatts of power, while shifting to second gear at the same speed, the engine drops to 5600 RPM, where it produces a maximum of only 62 kilowatts of power. There is a clear overlap between gear 2 and 3 in the acceleration graph. The lines cross at the point where the engine power is the same in both gears, namely 73 kilowatts at 6500 RPM in third gear and 73 kilowatts at 8800 RPM in second gear. At higher speeds, aerodynamic drag severely limits the acceleration potential of the car, distorting the shape of the acceleration curve so it no longer matches the shape of the torque curve. In lower gears, the car accelerates the hardest around, or rather shortly before, peak torque. This does not hold true for higher speeds, as illustrated by, for example, the third gear. At a certain speed, the acceleration drops below zero. The highest crossing point between the zero line and the acceleration curves is the top speed of the car with this gearing. To eke out every last bit of top speed, the gearing needs to be set such that peak power is achieved right at top speed. Practical example number 3. Torque versus revs. A recurring theme in heated automotive debates is big torquey engines versus small, high-strung, high RPM engines. To put this topic to rest, we make an extreme comparison. 2 naturally aspirated V12 engines, both making 300 horsepower. One is a 6-liter engine making 540 Nm or 398 foot-pounds of torque at 1800 RPM. The other one is a 2.3 litre engine making 251 Newton meters or 185 foot-pounds of torque at 7500 RPM. In this video we've already learned that power is what matters for acceleration, and the energy produced per combustion cycle, or torque, describes how that power is delivered. In order to compare the engines, we put them into the same 1.5 ton or 3,300 pound heavy car, and for now disregard the weight difference between the engines. The acceleration graphs do indeed look different because of the different shapes of the torque curves. Also, we can see that at lower RPM in every gear, the big V12 has a considerable advantage over the small, high-revving competitor. Why is this the case? The answer lies in the average power the engines produce across the rev range. The big engine has a downward sloping torque curve, producing above average power down at low RPM. The small engine produces below average power at low RPM. With both ending up at the same maximum power, that means the small engine produces less power on average. In fact, the big engine produces an average of 155.8 kilowatts, while the small engine only produces an average of 142.5 kilowatts. From this, we would expect the big engine to accelerate the car 9.3% faster. So under these specific circumstances, in this comparison, there is a clear winner. But hold your horses, all 300 of them. While you could think of engines that have these characteristics but still weigh the same, for example through turbocharging or supercharging, with the two naturally aspirated example engines in this case, it is not a realistic comparison unless we factor in their weight difference. Using automation to give us an estimate for that difference, the car with the small V12 would weigh 1,418 kilos or 3,127 pounds, while the car with the big V12 would weigh 1,572 kilos or 3,465 pounds. That is a difference of 154 kilos or 339 pounds, even though both engines are all alloy. You remember from the derivations at the start of this video that more mass directly lowers acceleration. Let us investigate how this affects the acceleration graphs. With more weight to pull, the big engine with plenty of low-end power no longer dominates this comparison. Quite the contrary. While it is still quicker to accelerate the car in the first half of first gear, the lightweight competitor starts to catch up and overtake soon after. Indeed, plotting both in the same graph reveals that acceleration is better for the big engine in the first half of the first gear only. After that, it loses out because when shifting gears, the small engine retains a higher power-to-weight ratio for the car, thus accelerating the car faster. How could we better illustrate this than with automation itself? In the game I have created the car and the engines we have been talking about. There are two trims to compare which are identical apart from the engine choice. One features the big V12 and the other the small V12 with the exact engine performance data we used. Both trims are geared the same way, which means that the big V12 trim has a final drive setting that is twice as long to end up at the same top speed. Neither gear spacing nor any other settings have changed. We are on high quality semi-slick tires and use an advanced limited slip differential to avoid having wheel spin. The final performance testing of the car shows just how similar in performance both solutions are. The biggest difference lies in the 0 to 100 time with just 0.1 seconds difference, where the big V12 plays out its advantage of having a lot of power available from low RPM onward. The difference in a 0 to 60 km an hour or 0 to 37 miles per hour would be massive though. That is the speed at which all following acceleration is quicker with the small V12 engine as it reaches its optimal power band and retains a higher power to weight ratio for the lighter car. Quarter mile times are exactly equal but come with different trap speeds. The standing kilometers slightly favors the small V12 with an advantage of 0.15 seconds and a 6 km/h faster trap speed. On the track, the weight difference makes the lightweight option superior, being 1.5 seconds faster around the track because of better handling and improved cornering performance. That difference could be minimized by proper suspension tuning though, and would be much smaller with a setup created specifically for the heavier solution. Overall, this example shows just how little absolute torque numbers matter. 540 Nm versus 251 Nm. Before seeing this video, many would have thought that isn't even a match. And no, even with the final gear ratio taken into account, the big V12 effectively still has more torque than the smaller engine, 270 Nm versus 251 Nm. Before wrapping up this video, let us address and answer some of the most common questions popping up. Question number 1. What do you feel, power or torque? Acceleration creates the force which pushes the driver into the seat. The counterforce from the seat is what you feel. Power is what accelerates the car, so it is always the car's power you feel. Question number 2. Can you feel torque at all? There's one situation I can think of where you can feel torque. With a big, powerful, longitudinally mounted engine, when you have the car in neutral and rev up the engine quickly, the car will slightly tilt to one side. That is the torque of the engine you experience right there. You can see it more clearly by watching the engine tilt in the engine bay when you rev it up. Question number 3. What about towing and off-roading? A common thing to hear is that you need a big, torquey engine for utility applications like towing or off-roading. We have learned that torque doesn't matter, so why are torquey engines usually preferred in utility applications? The answer is well illustrated in the comparison between the small and the big V12 in the practical example number 3. The most difficult thing in towing is getting up to speed, so you want to have a high amount of power available already at low RPM. You could always gear a small engine to be used for towing. Indeed, a tiny 100cc engine could easily tow a 50-ton heavy tank given the right gearing and enough grip. It would just be really slow at doing that because it produces so little power. Also, you could use a 19,000 RPM Formula 1 engine to power a truck. It would be stupid loud and wouldn't last long, but given the correct gearing, it would easily outperform on the task. For towing and off-road use, low-end power is what is the most helpful, and that is exactly what big torquey engines tend to provide. Question number 4. What about electric engines? Electric engines have a more or less constant power output across their very wide rev range. This makes them excellent for accelerating cars. Not having any limitations because of gearing means that acceleration is kept close to the theoretical maximum at all times. Question number 5. Which makes more power? 150 Nm at 9000 RPM or 300 Nm and 4500 RPM? They make exactly the same amount of power. Power is energy over time, and the product of torque and RPM is exactly that. This product is the same in both cases, so they accelerate a hypothetical car equally fast considering all other things being equal at that snapshot in time. Question number 6. What's better, more power than torque or vice versa? The question itself does make as much sense as, is it better to have more orange juice than oranges or vice versa? Power and torque do not have the same units, so you cannot compare them, but neither can you really separate them either. Let us form a question out of this, which actually can be answered. What shape of power curve is preferable? The answer to that is, well, it depends. Optimal performance comes from constant power, like from electric engines or with the help of a CVT gearbox. For the same amount of maximum power, looking at the torque curves can give us some indication of a car's characteristics. A flat torque curve usually is considered easiest to drive because of the predictability in behavior that comes with it. An upward sloping torque curve gives a surging feel to the car's acceleration and feels sporty, but requires more gear shifting and is harder to drive. Downward sloping torque curves usually mean better utility because of higher low-end power and require less gear shifts to be driven comfortably. Question number 7. What about crossover points in power torque graphs? Crossover points in power torque graphs don't mean much. They are purely an artifact of what units you choose to represent power and torque with. Using the metric units kilowatt and newton meter, the crossover point is at 9,551 RPM, while using the standard imperial units of horsepower and foot-pounds gives a crossover point at 5,252 RPM. To show just how arbitrary and meaningless this is, let us make our own power torque graph. We shall use the units of human equivalents, that is 80 watts per human, versus meter ounces, where 3.27 meter ounces equate to 1 Newton meter. As we can see, the crossover point now has moved to 2,504 RPM, which is just as meaningless as it is ridiculous. It is just an artifact of the units being used. Question number 8. Does the engine configuration change torque? The engine configuration doesn't change torque, or rather volumetric efficiency, much. Firing order and crank configuration can make a little difference because of exhaust flow and resonances. For example, a V8 flat plane in general is more exhaust efficient and produces more power than a V8 crossplane, unless the crossplane V8 has race exhaust wrapping around the engine to properly line up exhaust pulses. There are very little to no differences between I, V or W configurations when it comes to torque and power, apart from some of these special cases. Wankel and diesel engines are a completely different topic though. Question number 9. Diesels versus petrol engines. The main difference between diesel and petrol engines lies in the fuel characteristics and design fundamentals. Diesels produce more energy per combustion cycle on average because the fuel has about 11% higher energy density than petrol. They can use massive amounts of boost and compression without suffering the bad consequences a petrol engine would face. Also, they do not have as high pumping losses because of their lack of a throttle. These things all lead to higher volumetric efficiency and with that to more power output from the same engine capacity at the same RPM. On the other hand, a disadvantage of diesel engines is the slow flame propagation in the fuel-air mixture, which renders it inefficient to reach higher engine speeds. This all combined explains the usually high absolute torque values with a downwards sloping torque curve when compared to petrol engines. This is why diesel engines are so popular in utility applications, great low-end power and efficiency, but they lack a bit of a punch at the high end. Question number 10. What is torque steer? Torque steer has very little to do with engine torque, but rather with torque at the wheels. We are talking about forces here, so actual torque and not the energy per combustion cycle, which mistakenly is called torque, as you remember from the initial presentation. Hence, it is not a problem related to the topic of the video directly, so let me keep it short. Torque steer arises when you have unequal length drive shafts in a front-wheel drive setup. The more torque that is applied at the wheels, the more the steering gets upset and steers into a direction the driver didn't tell it to. As this requires a lot of torque to show up, it is usually a first gear problem. Hashtag first gear problems. Question number 11. Do torque or power affect handling? Power at the wheels affects handling through potential wheel spin. Tires give limited amounts of grip, which can be used for cornering or acceleration, or a mix of both in moderation. This is known as the circle of traction, where the length of the resulting acceleration vector made by combining the longitudinal and lateral acceleration is compared to the grip limit. Acceleration also directly affects weight distribution and therefore handling during acceleration. Actual torque can affect front-wheel drive cars with torque steer, but other than that there are no specific effects of torque or power on the car's handling. Question number 12. What about torque at the wheels? First, it must be made clear that engine torque has little to do with torque at the wheels. The gearbox serves as a torque converter and theoretically can give you any torque you want. 10,000 Nm of torque at the wheels is easily achieved by down-gearing the power put into the gearbox enough. Yet it doesn't help accelerate the car if that results in the drive shaft turning at 1 RPM. Hence, torque at the wheels is not necessarily a good measure to use unless a lot of relevant surrounding data is known. With that disclaimer in mind, yes, if you know torque at the wheels, the grip and slip angle of the tires, the speed of the car and the various resistances and friction, torque at the wheels lets you calculate the forces which accelerate the car directly. Question number 13. Oversquare versus Undersquare. A returning question is if for the same capacity engine a longer stroke produces more torque or not. To first order, this is not true, because capacity is what determines how much fuel-air mixture the engine can burn per combustion cycle. Again, with the difference between torque and torque in mind, that only the energy per combustion cycle matters and not torque in the sense of force and lever, it is clear that there is no intrinsic difference between Oversquare and Undersquare when it comes to energy production. However, when looking into the details and higher order effects, this is not quite true. For example, longer stroked engines tend to have a lower Helmholtz resonance frequency, enhancing torque at low RPM. At the same time, longer stroked engines tend to not rev as high as small stroke engines and hence are optimized for lower RPM where friction losses are lower. So overall, it is true in a second order approximation that Undersquare engines indeed have somewhat higher energy production per combustion cycle on average, but that is not due to the reasons commonly put forth. And this brings us to the end of the video. I really hope you enjoyed and learned something in the process, and if you haven't already, go and check out Automation to learn a lot more and try it out yourself. Alright, hope you enjoyed. See you guys next time.